So let's take a break here. Now, let's take this time to, before the break, I want to do the cost evaluation with you first. I want to give you 10 minutes to do the cost evaluation before proceeding further. And before that, I would like to announce something with you. I actually have sent you the email about this, but I just want to re-emphasize this. Now, don't miss the final exam. The final exam will be held next Thursday at 9:30 in the morning. Okay, it will be held on April 28, 9:30. And please enter the Zoom class by 9:20. Okay, the syllabus will be chapter 1 to chapter 11, including the mathematical notes. Okay, and please note the session that you are assigned to. There are 2 sessions, and each of you are assigned at one of the sessions. So don't go to the wrong room. Okay. Now, I know that the schedule is a little bit tight, so we are trying our best to support you in your exam. So we are afraid that you might not have have enough time to study. So we are trying to support you with what we can. Now, all the TA, they will continue to hold the consultation hours in their usual time next week. So if you have questions, you can just choose the consultation out of that TA and go to him by Zoom, and he will be able to answer a question. Now, TA Liang Qiujing, Kim is very good, a very kind TA. He promised to hold an extra tutorial. Now, because for these 2 weeks, we don't have exercise class, right? So about waves and about the vibration, you may not have enough practice. But Liang Qiujing is kind enough to hold an extra tutorial class with you on Monday. On Monday, 1:30 to 3:30, he will hold an extra tutorial for you. So I think he will just give you some practice question on vibration waves to do. So you will be more familiar with this topic before the exam. And this is the meeting ID, but anyway, you can enter from Blackboard. You can just get the Zoom class, and you'll be able to enter the tutorial. Now, I've also given you 2 past paper on the Blackboard with the solution, so you can use it as a practice. And if you find it difficult, anything you want to discuss with us, you just call us, okay? Now, homework 10 will be due next Tuesday. Sorry about the tight schedule, but since we have an exam on Thursday, I have to ask you to submit it earlier so that I can give you the solution at that evening. Okay, so you have enough time to study the solution. Okay, now we'll be answering your question by email or by Zoom. Just keep in touch with us. Okay, if you find any difficulty, you just email one of us. You just try to contact one of us, and we'll be able to help as soon as possible. Okay. Now, here comes the cost evaluation. Now, please go to the university email. I give you maybe 10 minutes to do it. You find the title of the email as Online CTE Questionnaire for the course PHY 111B. And the course title will be either University Physics 1 or Introduction to Mechanics, Fluids and Waves. Either one of them is the title. And the name of the teacher is Thompson Dominic. So please do it now. Okay, I give you 10 minutes to do it. on our discussions. So let's begin. Now, in the previous, in just the previous lecture, we have seen the picture, right? We have seen the pictures of the standing wave from the inside and tube that is open at both ends, and a tube that is open only at one end, right? So these are the wave pattern. But this is not a precise mathematical description of the wave pattern inside. We haven't derived a expression for the pressure wave and the displacement wave, and now we are going to do so. Okay, we are going to derive a standing wave for an open tube. Okay, now, suppose we have a pipe open at both ends, and the pipe extends from x equal to 0 on one end to x equal to L on the other hand. Okay, now so what will then be the displacement wave? We think that the displacement wave can be matched by such a standing wave, cosine omega t cosine kx. Now, provided that omega over k is equal to the wave speed of sound in air, then this solution will satisfy the wave equation. We have seen that the standing wave solution, it also satisfies the wave equation. The standing wave solution is just a superposition of two waves with the same frequency traveling in opposite direction. So they of course satisfy the wave equation. But that is possible only when omega over k is equal to v. Okay. Now you notice an important difference from our previous solution of a standing wave. In a previous solution, we use a sine kx to match the boundary condition. Now we use a cosine. Why do we use a cosine now for the displacement wave of sound? Because the tube is open at both ends. And that means the amplitude of the sound molecule vibration is largest there. So these two ends are the antinodes. And the easiest way to match an antinode at both ends is to use a cosine function, but not a sine function. If you use a sine function, the left end will be 0. The displacement at the left end will always be 0. You can't get the maximum displacement. But for cosine, you will get a maximum displacement at x equal to 0. So that's why we use a cosine. Now, so the first boundary condition is that at x equal to 0, the displacement is maximum. That's true because cosine k0 is 1. 1 is of course largest, right? How about the other end? The end x equal to L. The x equal to L will be a maximum, will be an antinode if cosine KL either equal to +1 or -1. Okay, so that is the condition. And that means KL should be equal to n pi. Okay, if cosine that is of angle is equal to +1 or -1, then it should be equal to, the angle should be equal to n pi, where n is an integer, integer larger than a positive integer. Okay, n equal to 1 correspond to 180 degree, n equal to 2 corresponding to 360 degree, n equal to 3 correspond to 720 degree, and all this angle give cosine KL equal to 1 or plus or -1. Okay, and so k is equal to n power of L, right? And then we can solve for lambda. Again, we find that lambda when is equal to 2 pi divided by k and is equal to 2L over n. Now this is exactly the same result as this case. Okay, lambda is 2L over n. Okay, but we just derive it more rigorously using the boundary condition. Okay, and the corresponding frequency will then be equal to kV. Now the k is n power of L, so the angular frequency is n pi v of L as before. Okay. Now, but we also have to find the pressure wave. We have the displacement wave with omega and k given by these two expression, but we still have to find the change in pressure along the tube. We have a formula for that. The formula is that the pressure wave P1 is equal to minus B, the round U round X, right? We have derived it at the beginning of our discussion on sound, right? So we just substitute the U into this expression, and when we do a straightforward differentiation on the factor cosine Kx, and that of course give me minus sine Kx, the minus sign cancel with the minus sign in front. The chain rule give me a factor of K, and so that become U0 BK cosine omega t sine Kx, okay? And I can further change the K and the B. I can further express them in terms of V and omega, and that becomes rho naught V omega U0, okay? Now you can see that goes as sine Kx. The sine Kx, if K is equal to n power of L, then the sine function will be 0 at both ends. Sine 0 is of course 0, but sine K n pi x over L at x equal to L, that becomes sine n pi. Sine n pi is always 0 also. So it guaranteed that at both ends of the tube, which is open to air, the pressure is the same as the atmospheric pressure. The pressure change there is 0. Okay, so this is a fundamental mode. This is a second harmonic, the third harmonic, and so on and so forth. Now you can see this wave pattern are exactly the same as a standing wave on the camera string, right? It looks exactly the same. But this exactly the same pattern is no longer a string vibrating now. It is the air molecule vibrating that produces a pressure. It is a change in pressure at different position. Okay, and the displacement wave are given by this. The different displacement wave are just opposite to the pressure wave. When the pressure wave has a knock at both ends, the displacement wave has an anti-knock on both ends. Okay. Now, so these two boundary conditions are satisfied, right? Okay, we have discussed before. Now, although I will not test you in the exam, it may be instructive for us to know how we speak. Okay. Now, people may think that vocal cord will be able to produce different sound. Now, this is not exactly true, because the vocal cords in our throat, it will only oscillate in the same way. Okay, it will not be able to change substantially to produce sound wave of different frequency. Okay, so it just when air just passes the vocal throat, the vocal cords, it just produces a periodic trains of air pulses, and that consists of sound wave of many different frequency. Okay, but those frequency and those amplitude will not change much, even if we speak in a different way. That the vocal cord is still producing the same composition of frequency and amplitude. Okay, so what makes us speak and with for different words and different sound? Now, it is a vocal tract, the oral and the nasal cavity, that modify the intensity of sound wave at different frequency. Because they are the resonant cavity, it's just like a sound pipe, like this, which is open at both ends or closed at one end. When you modify the shape of your mouth, and when you close your mouth, and when you open your mouth wide, you vary the shape and the dimension of this so-called oral and nasal cavity, or especially your oral cavity. Okay, and that produces a resonance with different with sound waves of different frequency, and you amplify those sound waves. And that's why you can produce different sound. You can produce different sound not because of the vocal cord can change the frequency, but because when you speak, your mouth can change shape, and your nose can change shape, just a little bit for the nose, but your mouth can change the shape and open it wide and close it, and all those changes give rise to different resonant frequency. Okay. And so it amplifies some of the frequency and suppress the other. Okay, and that's how we are possible to produce different sound. Now I have an interesting video for you to see. This is May Ann, famous actress, right? She inhaled some helium. Now, when she inhaled some helium, you know that helium actually has a smaller molecular weight than air. The helium molecule are very light. The helium atoms are lighter, much lighter than air molecule. And so sound wave actually propagate faster in helium than in air under the same pressure and temperature. Okay, so you see from the wave equation, the velocity of sound will become larger, right? Because may inhale some helium. So the sound will propagate faster inside helium. So the wave speed will increase. Okay, the wave speed increase. But how about the lambda? The lambda, the wavelength that get resonance, is fixed by the shape of the mouth and the size of your nasal cavity and the oral cavity. So they are fixed by the shape of your mouth when you speak. So lambda is essentially fixed. And that means we increase lambda fixed, and so the frequency will increase correspondingly with the wave speed. And so he will sound very interestingly because the frequency gets higher. The pitch of the sound will be getting higher. So let's see how May Ann speak. I share the sound with you.
中大嘅同學仔，你哋好，係時候要表演俾你睇啦。
Only you can take me 吹世嘅，我哋中大，難殺妖精鬼怪，唔好驚。I say I understand， 要全力對開都有問題就揾湯博士咯。拜拜。
Okay, so it's quite interesting to hear that. Okay. Now then we will have a discussion, a brief discussion only on sound intensity. Now the intensity of a sound wave at the surface is the average rate of energy transfer to that surface per unit area. So imagine now you have a sound source, and so it produces sound, and the sound wave will carry some energy, right? And the amount of energy reaching a surface per unit time is the power, right? So the power of sound is the energy reaching a surface per unit time. So it's a rate of energy transfer. If I divide that rate of energy transfer, the power divided by area, I get the intensity. And the intensity determines the loudness of sound you hear. So the intensity of sound we hear, the loudness of sound is here, is actually the power divided by the area. So if you have high power, of course, you have a lot of sound. But if your sound is concentrated on a small area, you also can produce a loud sound. Okay, so that's why it is proportional to the power, and it's inversely proportional to the area. Okay. And so the unit for power is watt per meter square. It's power per unit area. Now let's assume for simplicity, there's the point source. Now this is in fact not quite real, but let's assume it at the moment. The sound source is isotropically, can produce sound isotropically in all directions. And so the power of the sound source is PS. So this is the power of sound produced by the source. And they spread evenly in all directions. Okay. So when they reach a surface, which is at a distant R from the sound source, then the area, the sound power has already spread to a large area of area 4 pi r squared. This is the area of the sphere, okay, of the sphere that intercepts the sound energy, okay. So the power of the sound delivered divided by the area of the sphere will then be equal to the intensity of sound here heard at that position. Okay. Now, so immediately you can see that the intensity, is inversely proportional to R squared. So without any reflection from the surrounding, if the sound is spreading out isotropically, then the sound intensity or the loudness of the sound is inversely proportional to the square of the distance. And that is a kind of, we call inverse square law, okay? Now we have a special scale to measure the loudness of a sound. I think you have heard about decibel. Decibel is a unit, 分貝. Decibel is a unit for measuring the sound strength of a sound. In Chinese, it's known as 分貝. Decibel. Okay. Now the sound that the human ear can barely hear has a displacement. The air molecule has a displacement amplitude of 10 to the power minus 11 meter. Now this is extremely small. This is even smaller than an atom, right? It's a fraction of an atom. Okay, so this is the almost the smallest sound that you can barely hear. And for the loudest sound, the displacement is only about, it's just about 10 to the power minus 5 meter. We calculated that before in our classwork, right? Now, so there's an enormous range. You can see if the displacement have such a large difference of, say, 15 order of magnitude, then that would be an enormous range. But our ear can send, well, very sensitive. It can hear a sound wave of very different amplitude. Okay, so it is not that convenient to describe this change because of the large scale involved, the large number of magnitude involved. It is not convenient to describe it with a linear scale. So instead, we use a log scale. We use a log scale known as the sound intensity to measure the sound level. Okay. The sound level represents the sound intensity, but in a logarithm scale. And the so-called decibel, we call it beta. Decibel value is the 10 decibel. This gives you the unit multiplied by log I over I naught. I is the intensity of a sound at the position you heard it. And I naught is the reference, standard reference intensity. It is in fact the lowest intensity of sound that you can barely hear. Okay, so I naught takes the value of 10 to the power minus 12 watt per meter square. Okay, and beta has the unit of decibel. Okay, now you can see when I is equal to I naught, then beta is 0. And the 0 value of beta meaning that this is your hearing threshold. Below this hearing threshold, you cannot hear anything. And every 10 decibel, the intensity increased by 10 times. Now, why is it so? Now, if you consider a two sound of beta 1, and beta 2, they corresponding to the intensity I1 and I2 respectively. Okay. So if the difference between the two, if the sound level difference between the two beta is say 10 decibel, then how much will how much will be a difference in the sound intensity? You simply find the difference, right? So you have this minus this, right? But the law of logarithm tells me that if you have two logarithms minus each other, then that becomes what? Log I2 over I naught multiplied by what? This become reciprocal because it's become dividing, right? I2 over I naught divided by I1 over I naught. So the I naught get cancelled. That means the reference level does not matter. And you have a log 10 log I2 over I1. And so if you like, you can have I1 over I2. You take the power of 10 on both sides. Then you have this expression. You have 10 to the power, because you take the power of 10 on both sides to cancel the logarithm. So you have this. Now you can immediately see that if beta 2 minus beta 1 is equal to 10 decibel, if there's a change in 10 decibel, then it corresponds to what? When beta 2 over minus beta 1 is 10, this factor in the exponential become 1. And that corresponds to a 10 times in intensity. So that is the strength thing for log scale. When it changed by that 10 decibel, it does not change by just 10 linearly. It just changed by 10 times. Okay, so when you change by 20 decibel, when the sound level changed by 20 decibel, it corresponds to 10 times and 10 times, which is 100 times. When you change by 30 decibel, it corresponds to 10 times times 10 times some 10 times, and that is correspond to 1,000 times. So so there's the interesting thing about the log scale. It's not linear. Whenever you change a certain decibel, certain amount of decibel, that corresponds to how many times of change. Okay. Now, for example, if the beta is 40 decibel, then the sound intensity will be 10,000 times of the threshold sound level. Okay, of the threshold intensity. Okay. Now we also would like to have a brief discussion of solid sound wave in solid. Now when we discuss about strain, we have the wave speed V written as square root tau over mu, right? Tau is the tension on the strain and mu is density. And for sound in air, the sound has a wave speed given by the square root of the bulk modulus divided by rho naught. And we find that for our adiabatic model, for the compression without heat loss or heat gain, the bulk modulus is gamma P naught, the gamma, the adiabatic index multiplied by the equilibrium atmospheric pressure, and rho naught is the equilibrium air density. Okay. Now, when you look at these two formulas, you find some similarity. Although the quantity are different for different medium, but there are some similarity there. The similarity is that it is square root something divided by something. And that something in the numerator is always the elastic property of the medium. For example, the tension or the bulk modulus that specify how easy it is to compress the medium, right? So it is related to the elastic property of that medium. And in the denominator, you always have the density. Either it's a linear density for strain or the mass density for air or for other gases. Okay, so this is a general property. When you're talking about a mechanical wave, a mechanical sound wave, which is due to the vibration of air or vibration of solid, you always would have the wave speed being proportional to the square root of the elastic property divided by the inertia of the medium or the density of the medium. Okay. Now, but what is the equivalent of the elastic property, the bulk modulus in a solid? That is an interesting thing to us. Now, so here we have a simple model that allows you to derive the elastic properties of a solid. What is the corresponding quantity for the bulk modulus for a solid? Now we assume that we now have a metal rod of uniform cross section, and the metal rod is now under tension. We stretch it. You may have some weights on one end, and that produce some tension on the rod. Okay, and the tension force is now given by F. So the tension will cause the rod to the wire to expand a little bit. So there's a change in length, there's an extension. Now this change in length is very small because metal is actually quite hard, but it is still slightly deformable. So when you apply stress to some metal or some material, it will just deform slightly, but the deformation is too small to be seen with naked eyes. And so we assume a small deformation with small increase in length, that is delta L. Delta L is called the extension. Now the original length of the wire or the cylinder is L, and now under the tension we have an extension delta L. So we can define the stress as what? As a force divided by the area. So the stress is essential to the pressure. The force divided by the cross-sectional area of the rod gives you the stress or the pressure. Okay. Now for pressure, we usually refer to a pressing force. Here, because we are now referring to a stretching force, a force that stretches the string. So we don't call it pressure, but we call it stress. But essentially, the idea is the same. Either the stress or the pressure is just the force per unit area, the force divided by the area. Okay. And the strain of this wire or this cylinder is defined as a fractional change in length. If now I have an extension delta L and the original is L, then the fractional change in length is delta L over L. And experimentally, we find interesting thing is that we find that sigma and E, the stress and the strain of a given material, of a given wire, they are proportional to each other. So if you stretch it with a larger force, then you have a larger stress. The fractional change in length, the E, will also be larger. Now that sounds very reasonable. If you stretch stretches with a larger force, that of course produce a larger extension, right? That sounds reasonable. And the proportional constant between the two quantities is called the Young modulus. The Young modulus is defined as the stress over strain, the sigma over E. And if you write the sigma O and the EO, F over A is equal to E delta L over L. Now, what is the meaning of E? Now, E is a characteristic of the material. Different material have different characteristics. So what is the meaning of E? E is a quantity that plays the role of bulk modulus in a solid. If E is large, if the value of E is large, that means a very large stress is needed to produce a fractional, for a certain fractional change in length. And the material is said to be less ductile. So imagine it's very hard to deform the metal. So you need a very large stress to produce just a very small strain. And so in that case, the E will take on a very large value. And that means the material is not ductile, it's less ductile. If E is large, the material is less ductile. Ductile means that it is easy to deform. If the material is easy to deform, we call it a ductile material. Okay, and for the ductile material, you will expect a small Young's modulus. Okay, now these are the Young's modulus for some common material. Now steel is, although steel is strong, but it is actually quite ductile compared with other materials because their metal can deform a little bit. So steel has a Young's modulus of 200. Now you notice that the unit for the Young modulus is Pascal. Because the delta L over L, the strain does not have carry any unit, right? So the unit for the Young's modulus is the same as the unit of stress, which is the same as the unit of pressure. So it is measured in Pascal, but since the value is large, we usually measure in gigapascal, 10 to the power 9 Pascal. So steel has 200 gigapascal of Young's modulus. and you will compare with other material like concrete bone, you will find that steel is already very ductile compared with this material. So if you have concrete, for example, concrete is not a ductile material. If it's under stress, if you stretch it, then the concrete may break. Okay, but steel has a larger as a more ductile and it's not easily breakable. Now let's compare this with the air column. Now if we multiply, this is the relationship between sigma and the strain. Sigma is equal to E multiplied by delta alpha L. If we multiply the numerator and the denominator both by the cross-sectional area of the wire, the numerator then becomes a change in volume, and the denominator now become AL, the original volume. So the stress will be proportional to the fractional change in volume, V1 over V0, and the proportional constant is the what? Is the Young's modulus. Now this can be compared with gas. For gas, we have found that the change in pressure is proportional to the fractional change in volume, and the proportional constant is the bulk modulus. Now, but there's an important difference in these two equations. For the pressure change in air or gas, you have a minus sign because we are talking about the compression. The P is defined as positive when we compress the air. And when we compress the air, that of course will cause a decrease in volume. So P is positive means V is negative, right? And so there's a negative sign between the P and the V, okay? But for the solid that we have just described, the stress refers to the stretching force, and the stretching force will tend to increase the volume. So there will be no negative sign, okay? But you can see the Young's modulus in fact plays the role of the bulk modulus, okay? So the Young's modulus in solid is just about the same as the bulk modulus. And so you will expect the sound speed of a solid to be approximately given by this. The Young's modulus divided by the density, the square root. Now this expression is only roughly correct. Why? Because the Young's modulus are actually not the same as the bulk modulus. There are some subtle difference due to when the solid is deformed, the cross-section area actually change. So it's not that simple. But for simplicity, let us assume that is to be so. There's actually some correction to that. Okay, and so it's not exactly E, but in order of magnitude is approximately correct. And also, when we are discussing about this formula, we refer to the longitudinal sound wave, the compression and the rarefaction, right? We draw an analogy between the longitudinal sound wave in gas and the longitudinal compression and rarefaction in a solid. So what we refer to is a longitudinal wave. But sound wave does have a transverse component. The matter can have a shear component, and the shear component can propagate the vibration forward. And that shear component requires another treatment, and it's not included in this formula. So this formula is only approximately correct, and it's only correct for longitudinal sound wave in the solid, okay? Now, I may not have enough time to go through with you the Doppler effect. So I just would like to have a brief discussion with you, and to be fair to you, I will exclude this topic in your final exam. So in my final exam, I will only test to the section of sound wave in solid. I will not go further to Doppler effect. Okay, but for completeness, I still want to discuss the sound wave a little bit, the Doppler effect a little bit more with you, so that you have an understanding of it. Now, a common daily experience is that when an ambulance is approaching you, the sound frequency seems to be higher. The sound frequency you heard seems to be higher than this is at rest, right? And when the ambulance is receding away from you, the sound frequency will be lower. Okay, you will hear a sound of lower pitch. So the change is brought about by the motion of the sound source, right? The sound source, when it's approaching you, the frequency sound higher. When it's moving away from you, the frequency sound lower. And this is called Doppler effect. And Doppler effect, it actually exists for all wave motion, not only limited to sound. Now here is a simple explanation of a Doppler effect. Now, suppose you have a sound source. It may be a light source or a sound source, whatever source you like, as long as it's wave. So you imagine now the wavefront are propagating outwards from the sound source. But imagine that now the sound source is moving. Okay. So a person facing the sound source, the direction of the motion of the sound source, will find that the wave that he receives will get compressed. Okay, because the sound source is moving in that direction, right? So the adjacent wave will get compressed by the motion of the source. And so the person here in front of the sound source, he will hear a sound that will be at a high frequency. On the other hand, if the person is behind the source, a source is moving away from him, and the wave will get stretched. So the wavelength will be larger and the frequency will lower. And so the person here will hear a lower pitched sound. So this is a heuristic understanding of the Doppler effect. When you are facing the motion of the sound source, the wave gets compressed, and so you hear high frequency. And when you are behind the source, the wave gets reflected. It gets stretched. So you hear a sound of lower frequency. Okay. Now I think this is a better illustration. Let's just see the video effect. Now this is a stationary sound source, and the wave simply propagate forward evenly in all directions. Now you have the sound source moving. You can easily see that the wave on this side, on the right side, get compressed, while the wave on the other side, they get stretched. So there's a difference in wavelength on both sides, and that gives rise to a difference in frequency. Now, what we say is about the motion of the sound source. Now let's talk about the motion of the observer. Suppose you have a sound source which is stationary in a medium. Suppose you have some, for example, a loudspeaker, for example, which is stationary in air, and it gives out sounds in all directions. Okay. Now, if you have an observer moving towards the source, then you will be colliding with the wavefront more frequently. Now, the wavefront are spreading out. They are evenly spaced because the wavelength are fixed, right? The wavelength is fixed by the frequency and by the property of the medium. So the wavelength, the separation of the wavefront will be even. And if you have a person who is moving towards a sound source, he will collide more oftenly with the wavefront. And so he hears a sound with a high frequency. And if the person is now moving away from the sound source, the sound wavefront will be chasing him. So he will be colliding less frequently with the wavefront. So he will be hearing a sound with a lower pitch or lower frequency. So again, if the person is moving towards it, he hears high frequency. If he's moving away from it, he hears a low frequency. Now the result is almost the same as the moving source. When the source and the observer, they approach each other, either the source move or the observer move, the frequency get increased. If the sound source and the observer, they are receding away from each other, no matter it is a source moving or the observer moving, the frequency get decreased. Okay, so that is the essential points about the Doppler effect. Now let's talk about the general formula. The general formula for Doppler effect, I emphasize that this formula is not applicable to light. Okay, because if you talk about light, then you will consider, when you consider light a motion that is close to the speed of light, then it requires the use of special relativity. There's a time dilation. So this formula is not applicable to light, but it's applicable for all kinds of sound at low speed. Now, F prime is the observed frequency, and F is the emitted frequency. That means if a source emit a frequency, emit a sound with frequency F, then if the source is moving or the observer is moving, the observer will observe a frequency F prime. Okay, so there's a different. The middle one is the factor that's caused a different. Now here the V here is the speed of waves in the still medium. And what is V naught? VO is the velocity of the observer or the detector. And in the denominator, the Vs is the speed of the wave source. So VO corresponding to the motion of the observer, while Vs correspond to the speed of the source. Now, whether we choose a plus sign or the minus sign depends on the direction of the source on the observer's velocity. Okay, but how do we choose it? Now, I prefer you not to remember the plus sign or the minus sign by the equation itself. I prefer you to use your physical sense, use physical understanding to choose the sign. Because to remember the plus sign and the minus sign is always quite confusing. So it would be better for you to memorize the physics behind and use your physics understanding to choose the plus sign or the minus sign here. Now, the first thing to note that is when the source or the observer speed is much more than the wave speed in the medium, then I can neglect V0 and Vs relative to V. And that means the Doppler effect is negligible. Okay, so that is the first observation. Because when I ignore VO and Vs, it will become V divided by V, right? And that's 1. So F prime will then become F. And that means the Doppler effect is negligible. Now the observer speed is in the numerator and the source speed is in the denominator. So how to choose it? Now when the observer is approaching, now the observer goes in the denominator. When the observer is approaching you, F prime will increase, right? How to make F prime larger than F? You take the plus sign. If you take the plus sign, then the numerator will be larger, and that makes F prime increase. And so for the case when the observer is approaching the source, you should take the plus sign. And on the other hand, if the observer is receding away from, is moving away from the source, you should take the negative sign for V0. Is that clear? Now, how about the source? If the source is approaching you, then F prime will increase, right? But the Vs is in the numerator, is in the denominator. So how to make this factor larger? How to make this factor larger as a whole? The trick is to take a negative sign. If you take the negative sign for Vs, V minus Vs will be smaller. And if you have a smaller thing in the denominator, that means this factor will as a whole be larger. And that will make F prime larger than F. So in order to make F prime increase, you should take the negative sign for Vs. On the other hand, if the source is receding away from you, then you should take the positive sign for Vs. Okay. So in here you memorize the physics, but not only the equation. Because I don't have enough time to discuss about all the content, so I just skip the proof. I would like to end my lesson with only one or two examples of applying the Doppler effect. I just skip the proof for the direction for observer and the source moving. I just give you this example before we end this lesson. Now, suppose the bat is chasing a moth. It's well known that the bat is able to emit some ultrasound. And when those ultrasound are reflected from the prey, from the moth, when he detects this reflection, he can distinguish the difference in the frequency between the incident and the reflected wave. And from this information, he can estimate the distance from the moth, and he also estimate the speed, the relative speed between him and the moth. So if he is not flying in fast enough, he will increase in speed to chase it. Okay. Now we suppose a simple example. The bat velocity is 9 meters per second, the moth velocity is 10 meters per second, and they're flying in the same direction. And the ultrasound of frequency 82.352 Hertz is emitted by the bat at a sound speed of 343 meters per second. And the sound wave will hit the moth, right? And so I require you to find the frequency of sound wave falling on the moth. And after the sound wave hit the moth, it reflects back. So during the reflection, the moth will become the sound source. And when the wave reflects back, the bat will hear that reflection. And so the bat now becomes the observer. So you just reverse the roles of the bat and the moth in the reflection. Okay. Now let's take the forward motion first. Okay, let's take the motion of sound from the bat to the moth first. We go back to this formula. Now, since the source is moving towards the bat, the bat is moving towards the moth, and the bat is the source, right? So the frequency will be increased by that, right? So according to this formula, what should we take? The source is moving now, and I want to make f prime larger. So I should take the negative sign, because the negative sign will decrease the denominator, and that makes the whole factor larger. So that's why that means I should take a negative sign for Vs. Now the moth is flying away from the bat, and that will make the frequency smaller. And since I'm in a denominator, VO is a denominator, right? So to make the f prime smaller, I will take a negative sign. So both signs should be taken negative, right? For the bat, the negative sign here will make the frequency larger because it's flying towards the moth. But for the moth, the observer, I should also take the negative sign because it's flying away, and they make the frequency smaller. So both of the signs should be negative. Okay, so this is the situation. And we just substitute the wave speed and the respective speed of the moth and the bat. We find this frequency. This is frequency of ultrasound falling on a moth. Okay. Now, and then the moth will act as a source when it reflects the wave back. So the source frequency now becomes this value. Okay. Now the bat is moving towards the moth, right? So it tends to increase the frequency. Now the bat becomes an observer. So in order to increase the frequency, you should choose a plus sign. So we should take the plus sign for VO. The moth is, however, moving away from the bat. The moth is now the source, right? And that will make the frequency to decrease. How should we do that? Increase the denominator. So we take a positive sign at the denominator. Okay. So both of the sign will be positive. And when we multiply this value of the frequency, we get the frequency heard by the bat. This is a reflection sound, ultrasound heard by the bat. Okay. So I think there's another example. This is a classwork, but I think you can do it yourself. If I don't want to repeat more, I think you'll be able to use the rule that I introduced you to work on this question. Okay. For this derivation, if you are interested, I encourage you to look at it yourself, but I'm not going to teach it because the time is over. So I better stop here, not to overtime too much.